Now here we'll define the least squares regression line. It's also called the regression line or the line of best fit. When we are trying to find the relationship between two variables x and y, x is called the explanatory variable, y depends on x, and it's called the response variable. The first step to finding the relationship between two variables is to first collect data and make a scatter plot. So once we have data, we first make a scatter plot, and once we make a scatter plot, what we can see is if there is a pattern that these points are forming. So if there is a pattern, and if the pattern is linear or a straight line, then the next step is to find correlation. It's appropriate to find the correlation. The numerical summary R describes the strength of the linear relationship. The relationship has to be linear to begin with, and only then can we calculate R, the correlation, which gives us the strength of the linear relationship between the two variables. So it's appropriate to calculate R only if the relationship is linear. Now, from the scatter plot, we know we can find the form, which is linear in this case. Direction, so when I say direction, it can be positive or negative. In this case, the direction is positive because as we go from left to right, the line that we are imagining through these data is increasing or rising. So as x increases, y increases in this case. So that is direction. Direction can be positive or negative. We can say something about the strength. I would say here that the strength is roughly strong. I would say it's strong. But from the graph, the strength of the relationship cannot be determined for sure, because as we change the scale of the graph, the relationship might appear stronger or weaker depending on the scale. So the strength of the relationship is basically something that we can get for sure from the correlation R. R is a number that lies between -1 and 1, and the correlation R is the numerical summary that describes the strength of a linear relationship. Only if it's linear, remember, can you use the numerical summary R. Numerical summary is just a fancy word for a number or a set of numbers that describes something about the data. So in this case, the numerical summary correlation describes the strength of the linear relationship. So the regression line is the line that best fits the scatter plot, the data set. And it's a line that minimizes the sum of the squares of the vertical distances. And when I say vertical distance, it's this. We're looking at the point, vertical distances from the point to the line. So just draw a vertical line from the point, which is the real world data, those crosses, to the regression line. So it is a line that minimizes the sum of the squares of the vertical distances from the points to the line. Now, the regression line can be calculated using the means and standard deviation. So mean would be x bar. So that would be for the explanatory variable, x bar for the response variable, standard deviation for the explanatory variable, standard deviation for the response variable, and correlation. These are the numbers that go into the calculation of the regression line. Now in this class, we are not going to calculate the regression line from scratch. We're going to either use the calculator or use Crunchit to construct the equation of the line or to calculate the equation of the line. You do not need to do this from scratch, but just be aware that these are the numbers that go into the calculation of the regression line. So B, the slope, is correlation R times S subscript Y divided by S subscript X. So S subscript Y is the standard deviation of the response variable, and S subscript X is the standard deviation of the explanatory variable. Now remember that the regression line is a line that best fits the data set, and it doesn't have to pass through any of the data points. So when I say data points, these are real world data or observed values, or the observations from our study or experiment, and the line doesn't have to pass through any of these points. Now we use the line to make predictions or make estimates of y given an x. So this is how we do it. Suppose I want to find the value of, let's say this is between 0 and 10. Suppose I want to find the estimate, the value of y based on the value of x. If I want to estimate, then I go up to the line, which means I plug in the value of x into the line and then figure out a value of y. This is called the predicted value. I call it the predicted value because the prediction comes from the straight line. I plugged in, so I geometrically, what you see is the geometry of it, but in algebra I would plug in the x into the line and figure out the value of y to get a prediction or an estimate. The actual value goes up to this point, the observed. So this would be the observed value. For the observed value, I have to go right up to the actual data point from the study, and that would be the observed value from the observations in your study or experiment. Predictions are from the regression line. Regression lines are used to make predictions. The observed value is from the actual data point. Now, the next question says, does the predicted value y have to be equal to the actual value? And clearly that is not the case, as we've seen here in this example. Here is the predicted value, which is y hat. The value of the function is always the one on the y-axis corresponding to the x that you plug in. And this is your observed value. Notice that they are different. The observed value will be close to the predicted value if the correlation is strong, which means if the correlation is strong, then our predictions are close to reality. If the predictions are strong, if the correlation is strong, then the predictions are good. Now, in chapter 4, it's very important to keep the explanatory variable and the response variable straight. In chapter 3, when we were calculating the correlation, it really didn't make a difference if you switched the explanatory variable with the response variable, but in chapter 4, you have to be extremely careful. Based on what we want to predict, pick the response variable. What we want to predict is the response variable, and the other variable would be your explanatory variable. Now, the slope of the regression line is calculated using this formula, r times s subscript y over s subscript x. S subscript y is the standard deviation of the y values, the response variable values, and s subscript x is the standard deviation of the x values or the explanatory variable values. Remember that standard deviation is always positive, so the slope of the line always depends on the correlation. So if the correlation is positive, then the slope is positive. If the correlation is negative, then the slope is negative. And clearly that should be quite obvious from our previous discussions. Remember that if we plug in x bar into the equation, and these are the details of the work, but the important thing to remember is that the point x bar, y bar, remember that x bar is the sample mean, the mean of the x's, and y bar is the sample mean for the y's, and x bar, y bar is definitely a point just based on how the least square regression line is constructed. Now, another important fact to know is correlation R describes the strength of the linear relationship, whereas the square of R is defined as follows right here. The square of R is the fraction of the variation in the values of y, fraction or percent of the variation in the values of y that can be explained by the regression line. So that's the definition of R squared. So for example, if correlation is 0.9, then it's a very strong correlation, which means our regression line will give very good predictions of the response variable. Now, if I say what percent of the variation of the response variable can be explained by the regression line, then we calculate R squared, which is equal to 0.81, which means that 81% of the variation of the values of the response variable can be explained by the least square regression line. You just have to remember this definition. So if the question says what percent of the variation in the values of y can be explained by the regression line, by the least square regression line or the regression line, then all you have to do is take R, square it, change it to a percent, and say approximately 80% of the variation of the values of y can be explained by the regression line, either fraction or percent. But usually we use the term percent in this context. So about 80% would be 80 over 100, which is 8/10, which is 4/5. About 4/5 of the variation of values of y can be explained by the regression line.